Hey guys, how you doing? This is Coach Scott. This is our second video in Unit 6 where we start talking about what these IMFs are, intermolecular forces. So there's going to be three types of intermolecular forces. And I'm going to say this word now, but we don't want to use it again. We don't use this in higher levels of high school chemistry. In college, you may encounter this term. It's one of my favorite terms, actually. These intermolecular forces are known as van der Waals forces. Van der Waals forces. And these are the forces that will bond these molecules together. There's three types that we're going to study. Dipole-Dipole interactions, Ldfs, and hydrogen bonding. Ldfs are London dispersion forces. So, a dipole, we talked about this before the break. A dipole is a polar molecule. And what makes a molecule polar? All right, when there is a difference of electronegativity, right, where that one atom will pull those electrons more to it than the other, that becomes a nonpolar. These are the numbers we use. A nonpolar covalent, the difference was pretty small. Polar covalent, a difference of about 0.2 to 1.6. Ionic, anything above 1.7. Okay, and they're between a metal and a non-metal, pretty much. That's the only way you can get that difference. So, hydrogen fluoride, hydrofluoric acid, is an example of a polar molecule, or a dipole. The fluorine end of the molecule is got more electron density than the hydrogen end, and because the fluorine has a higher electronegativity, and it's going to hold on to that shared electron more so than the hydrogen. So we'll put this with this little symbol like so. This designates the dipole. What do I mean by dipole? Two poles, right? The positive end is the one that's going to be more positive part of the molecule, and the arrow will point toward the more negative end. So molecules that have a permanent dipole are attracted to each other. The positive end of one is attracted to the negative end of the other, and vice versa. All right? And these forces are only important when the molecules are close to each other. They've got to be pretty close for them to be attracted. Now, only polar molecules will have this dipole-dipole interaction, or this IMF. So if you look at our little picture right here, the red end, all right, okay, is more a little bit different. Now these are the same type of pole, and they're going to repulse the other end, whereas this blue end is attracted. So the repulsion interaction is the black lines. The red lines are where there's the two opposite ends are attracted to each other, and that's your dipole-dipole interaction. So the polarity of a molecule is measured by a new term, a dipole moment, or I think that's mu. Mu, the Greek letter mu, looks like a little U. All right. The more polar the molecule, the greater the dipole moment. Also, the more polar the molecule, the stronger the attraction is between the molecules. And because there's a stronger attraction, it's going to take more energy to separate those molecules. Therefore, it will have a higher boiling point. So we got some cool molecules here: acetonitrile, acetaldehyde, methyl chloride, dimethyl ether, and propane. Okay, if you look at their dipole moments, the higher the dipole moment, the higher the boiling point. This is in Kelvin, right? And there's the molecular weight, but really it's that dipole moment that makes these the boiling point so high. So a type of test question would be something like this: which of the following molecules will have the highest boiling point? Well, looking here, I'm looking at the dipole moment, so I would have to say what? Pause. That would have to be D, because it has the highest dipole moment. Which would have the lowest dipole moment? Well, let's find the substance with the lowest dipole. That would be the CH3, CH2, CH. I think that's propane. And I think you guys get this. So those are the dipole-dipole interactions. Ldfs, or the London dispersion forces, occur between all molecules. And these result from the fact that the electrons are constantly moving around an atom. We know that, right? And that what that means with a gazillion atoms out there, with a gazillion more electrons, sometimes those electrons are going to be on the same side of the molecule. And when we're on this same side, that's going to induce a dipole, and the molecule will become slightly polar. One side will be negative and the other positive. Then the molecule will act like a dipole. This doesn't happen very often, right? But it will happen. So this polarization creates an electric field that oppositely polarizes another molecule nearby, which means that they're going to be attracted to each other for a moment, a slight moment in time, until the electrons move around. So that would be an induced dipole. So let's look at helium. Now the electrons in the helium are going to repel each other, right? But sometimes they're going to end up on the same side of an atom. All right, when this happens, then the atom is polar, with an excess of electrons on one side and a shortage on the other. So when those electrons right there go on that side of the molecule, then you're going to have a dipole, which can induce another one, right? Because there's another helium atom near it. All right, it's going to become polarized because that positive nucleus of that instantaneous dipole, they call it, will pull those electrons away from its neighbor, and that's going to make another dipole for a moment. All right, so these are what we call instantaneous dipole, boom, and an induced dipole. These don't happen for very long. Now, these forces are present in all molecules, whether they're polar or nonpolar. All right. So we call the tendency of the electron cloud to distort itself, we call it the polarizability. Now, it makes sense. The more electrons you have, the more chance that you can induce or have an instantaneous dipole, because you got more electrons to move to one side. And because those are going to be the larger molecule, these become more polarizable. Molecules with more electrons experience stronger Ldfs. It sort of makes sense if you stop and think about it. So now we can use what we know about Ldfs to understand what's going on with boiling point. All right, so let's look at the halogens, and then let's look at the noble gases. Fluorine, F2, is a nonpolar molecule. It has 18 electrons. It has a very low boiling point, 85.1 Kelvin. Chlorine, more electrons, again, nonpolar. It has a slightly higher boiling point at 238.6. Bromine, further down the periodic table. All right, it's got 70 electrons, nonpolar, but you can see that it has a higher boiling point. Iodine, the largest halogen, 108 electrons, it's going to have a higher boiling point because of the Ldfs, or the instantaneous dipoles. All right, the greater the number of electrons, the more polarizable the particles are, and this will create stronger London dispersion forces. If you look at the noble gases, same O. Helium, that's not very high, 4.6, above 0 Kelvin. Xenon, the largest noble gas, 54 electrons. Okay, it's got 166 boiling point because of all the excess or extra electrons around it. So of course we know now that all molecules have LDFs, so that would be false. Just go through these relatively quick. Okay, and molecules with more electrons experience stronger LDFs. That is true. Which would have the highest boiling point? This would be the largest halogen, and of course that would be iodine. Which would have the lowest boiling point? That would be the smallest halogen, and that would be fluorine. Which would have the highest boiling point? Of course, that would be xenon. Just move through these quickly. And helium would have the lowest boiling point because it only has 2 electrons. So, if we look at these dipole-dipole interactions and we compare them to LDFs, the dipole, if we've got 2 polar molecules and they're about the same size, there's going to be more dipole-dipole interactions. That's going to be the dominating force. Now, if one molecule is much larger than the other, all right, the Ldfs will likely, keyword likely, determine the physical properties because it's going to have a greater attraction repulsion because it's going to have more electrons to induce that dipole. If the molecules are nonpolar, then we know that the Ldfs will dominate since all molecules are going to experience these dispersion forces. So, let's look at another one. This is a special type of IMF called hydrogen bonding. So this graph shows the boiling points for 4 polar and 4 nonpolar compounds. Now, if you look at the nonpolar series, that's methane and CH4SI4, whatever that is, 10 tetrahydride. The boiling points are going to increase as we have more electrons. If you look at compare that, that's got more electrons than that one. Excuse me, this has less electrons than that one, and we're going down the group is what we're doing, the carbon group. And then, of course, the boiling point will go up because these are very nonpolar compounds. Okay, these are stronger dispersion forces due to what? Because greater polarizability. Now, okay, these are the group 16 hydrides. These are polar compounds. There's H2O, H2S, H2SE, H2TE. Now, if we go from H2S to H2TE, the boiling points are higher than the nonpolar series. See the difference? This makes sense, okay? And then the boiling points are going to increase with the greater molecular weight or the greater number of electrons. That's expected. But we have an anomaly. What's going on with water? That's weird. Water should be down here somewhere. But if we base it on the molecular weight and the electron number, it should have the lower boiling point. But it doesn't. It has one of the highest boiling points at 100. And this is one of the miracles of creation. There's a special dipole-dipole interaction called hydrogen bonding. It's really not a bond. It's an intermolecular force. And this happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. I call it FON, F-O-N. So when hydrogen can bond to an oxygen, those little dots right there, that's a very, very, very strong dipole-dipole interaction called hydrogen bonding. And because it's such a great attraction, therefore H2O will have a higher boiling point because it'll take more energy to separate those molecules. And this happens whenever there's a nitrogen, there's ammonia, NH3, and water. There's a very strong hydrogen bond there, okay? And it will happen with fluorine, oxygen, and nitrogen, okay? And then there's a hydrogen available. There can be a hydrogen bond. Now, this happens because there's a higher electronegativity and a smaller radius of nitrogen, oxygen, and fluorine. They're pretty electronegative. So when the hydrogen is bonded to one of these, these very electronegative elements, the hydrogen nucleus becomes exposed, okay, and it becomes almost a proton. Okay, so let's see if I can get this thing going. It does. So let's pause and we'll watch this little video. Oh no, they got rid of that one. Okay, that's a flash thing, so we won't see this really cool animation. All right, so water is one example of a substance that is less dense in the solid state than in the liquid state. There's not very many. Usually the solid is more dense than the liquid. That's good, right? Because ice will float on liquid water. If it didn't, there would be a different life on Earth because, all right, the lakes and ponds and oceans would freeze from the bottom and the fish could not survive the winters. All right. Now, this hydrogen bonding creates the space, and I've got a little molecule we'll see in class that explains why there's such a low density. Let's see if I can get this one going. It does. So we'll see this, pause, and I'll show you in just a minute. Okay, so this is a nice little how liquid water, all right, and I'll give you this little, if you look at water, they'll come together, right? They'll condense, and if you notice the positive and the negative edges come together. So let's see if I can go back on this one. And then let's see how water will transition from ice and back and back and forth here, right? All right, let's do this. Okay. All right, so that's ice. Okay, you see how it's got its deal there. Now let's look at the water. So water is freely able to flow and do its thing. Let's see what happens here. All right, so those are just the sticks. Let's see what happens. Let's see what happens when we freeze. All right, so we're moving and we're going to freeze it into solid water. The molecules form that three-dimensional state, and you see it's making those little hexagon type things, and that gives why water is less dense as a solid than liquid. Let's see how it melts. So we're adding heat to it. It starts to separate those molecules and they go into their liquid state like so. Pretty cool. And we'll see this in class. Okay, so that was a pretty cool little demonstration. So let's talk about it real quick. Which of the following molecules has hydrogen bonding as one of its intermolecular forces? Well, first of all, we've got to have the fonts, F-O-N. Well, there's only one with F. I don't see N's or O's, so hydrogen fluoride or hydrofluoric acid would be the one with hydrogen bonding. Which the following has hydrogen bonding as one of its IMFs? Well, what am I looking for? I'm looking for F-O-N, so I believe that would be D. F right there, because it's pretty strong. That would be the one. Okay. And that's not an external one. That's more of a center molecule. So, of course, it would be D. So, there's a fourth minor intermolecular force, and these occur between ions and molecule. Okay, and we're going to talk about it. All right, and this is sort of important as we start talking about solutions. So you do need to understand it, right? And these are ion dipole interactions. Now, we don't consider those to be intermolecular forces or a van der Waals force. Ooh, don't say that again. Because it's between an ion and a molecule. So it's not an IMF. So the ion dipole force will cause the ionic substance to dissolve in polar solvents. So I've got an anion right there, and because it's so strongly negative, it's going to pull, all right, those polar parts of the, let's say that was sodium, this is water, so it's going to pull that sodium cation apart. Excuse me, that'd be the chlorine. These would be the positive ends of the water. It's going to pull it in there. So this would be the sodium cation, and they're going to go around and grab it. Okay. So coming down to the end, this is a nice little flow chart to figure out what do we have. If ions are involved, no. Then we've got to ask, are they polar molecules are involved? No. Then we just have dispersion forces, Ldfs. If we have polar molecules involved, then we got to ask, is there a fond there? Are hydrogen atoms bonded to a nitrogen, oxygen, or fluorine? Yes, then we could have hydrogen bonding. If no, then probably the determining force would be a dipole-dipole force, like those. Are ions involved? Are polar molecules and ions both present? Yes. Then we could have ion dipole forces like salt water, sodium chloride dissolved in water. No. Then we just have ionic bonding like NaCl or potassium iodide, or those that we studied earlier in the year. So a summary of our three IMFs. We have Ldfs, that's the weakest IMF. Dipole-dipole is the strongest IMF, and then of course hydrogen bonding is the strongest IMF. So what types of molecules? Ldfs are in all molecules, even the ones with hydrogen bonding is there. Dipole-dipole, only polar molecules. Hydrogen bonding, only polar molecules with hydrogen bonding to FON, F-O-N. And when we want to check it, let's look at the number of electrons, okay, for Ldfs. Then we can, for dipole-dipole, look at the given dipole moment. Hydrogen bonding, look for an HN, HO, or HF bond. If they're not there, well, no, it's not going to happen. Okay. Which of the following has London dispersion forces as only IMF? So we're looking at a big molecule. We're looking at something that's not polar, pH 3. I think that would be D, silicon tetrafluoride. And it is. Which of the following of these substances would have dipole-dipole interactions? Well, H2O will, but it's got something else going on. CO2, that's more of a linear molecule. No, that's nonpolar. That's polar, so I think there would only be two. C, H2O and ammonia. Which of the following molecules will have the highest boiling point? Well, that's going to be H2O because it has hydrogen bonding. And then sometimes, like I know these things, which is polar, which isn't. Sometimes you may have to draw a Lewis structure and figure out what type of structure it has. Which of the following diatomic molecules has the highest boiling point? Highest boiling point. So there, what are we looking for? We're probably looking for the largest molecule because all of these are non-polar, and yeah, there's no hydrogen, oxygen, hydrogen fluoride. So I'm going to say that would be B. It's the largest molecule. It has more electrons. Which has the lowest boiling point? Well, that's going to be hydrogen because it has the least number of electrons. Which one of the following derivatives of methane has the lowest boiling point? We're going to be looking, CH4, we're going to be looking for the smallest amount because these are all nonpolar. I'm going to say that's going to be B, and it is because fluorine or the carbon tetrafluoride is, well, has less molecules than less electrons than any of the others. And which one has the highest boiling point? I think iodine is above bromine, and it is. So that would be carbon tetraiodide. Okay, guys. Well, that's IMFs. Those are the types that we're going to study, the types that affect how we live life. And yeah, we'll talk more about these later, and you'll have lots of practice. Okay, guys, this is Coach Scott saying have a great day. I'm out of here, and we'll see you soon. Bye.